Welcome to the last screencast on biomolecules. This one deals with, first of all, water, and then looks at the difference between triglycerides and phospholipids, and also a little bit at cholesterol. And then what we do is we look at the tests for carbohydrates, sugars, non-reducing sugars, and starch, and proteins, and fats. Okay, and we also look how we can use the Benedict's test as a quantitative test to work out the concentration of a reducing sugar in a solution. Okay, so just dealing with water first of all on this first slide. There's an awful lot on this slide, and I'll quickly go through it, and then there's a little video we can watch. Okay, so the key thing here is the idea that water is rather an odd molecule, in that, as we know, it's oxygen bound to two hydrogens, but because of issues with chemistry, I don't want to explain it any further than that. What happens is the electrons, which are shared in a covalent bond between hydrogens and oxygens, are pulled towards the oxygen, leaving the oxygen more negatively charged with respect to the two hydrogens. Okay. What this does is that water molecules are attracted to each other, i.e. the hydrogens of one water molecule will be attracted to the oxygens of another. Okay. These bonds aren't as strong as the covalent bonds within a water molecule, but they're still nevertheless relatively strong bonds, and they are called hydrogen bonds. Okay, and these hydrogen bonds, okay, which hold water molecules together, explain all sorts of rather odd physical properties of water. Okay, the first odd physical property of water is that it's a liquid at all at room temperature. Most similar sized molecules are gases at room temperature. When you think of hydrogen sulfide, ammonia, and all those things which have similar molecular or formula mass to water, yet they're gases, whereas water is a liquid. The reason water is liquid is because of these hydrogen bonds which hold water molecules together. Okay, these are intermolecular bonds, hydrogen bonds. Okay, one of the other facets of these hydrogen bonds is that when you heat water molecules up, okay, you've got to overcome these hydrogen bonds for the molecules of water to increase their kinetic energy, i.e. to allow them to move around. Okay, this results in water having what's called a high specific latent heat, which basically means there's an awful lot of energy required to heat a body of water. Okay, and the consequence of this, okay, for organisms is that because organisms are primarily made of water, their temperatures remain fairly stable despite quite wide fluctuations in ambient or air temperature. Okay, so an organism as large as ourselves, okay, we can survive in quite cold climates and fairly warm climates, and it doesn't have a huge impact on our body temperatures because of this specific latent heat, because a huge amount of energy is required to raise the temperature of a body of water by a rather small amount. Okay, so that's called specific latent heat. It also has an impact on the environments that we live in, oceans and so on. Despite huge fluctuations in air temperature, there's actually very small fluctuations in temperatures of oceans, again because of this specific latent heat, which is very important for the life that lives in water. Okay, so specific latent heat and its consequences on biology. Okay, next one to consider is latent heat of evaporation. Okay, this is the amount of heat required to convert liquid water into water vapor, and again there's an awful lot of heat required to do that. Okay, and we make use of this in biology as a cooling process. So sweating, you remember sweating, we would have looked at GCSE. The idea is that our body heat is used to convert sweat into vapour, okay, and then so doing takes a lot of body heat with it, okay. One of the reasons it's so effective is because of the high latent heat of evaporation, i.e. a lot of energy is required to convert our liquid into a gas. Leaves do the same. The whole idea of the transpirational flow of leaves is to maintain leaves at a temperature which is optimum for enzymes. Okay, leaves, if they were exposed to sunlight all day and there was no transpirational flow, very soon all the water in the leaves would reach boiling point and denature all the enzymes. Okay, but the evaporation of water from the stomata of the leaves acts as a cooling system. Again, large latent heat of evaporation removes a lot of heat energy from leaves. Okay, so again, looking at the physical property, latent heat of evaporation, and relating to that to some aspect of biology. Okay, it's important that you do that in any question you're given. The next one looks at cohesion. Because of the hydrogen bonds, water molecules stick together. The result of this is that a column of water has high tensile strength. Okay, that means it can't be pulled apart. Okay, and that's hugely important for that transpirational flow that you learned about in F211. Okay, water moving up through leaves. Okay, there's a huge pulling force which comes from the leaves, which is transmitted all the way down to the roots because of the water having a high tensile strength, which is because of the water molecules being bound to each other by these hydrogen bonds. Okay, so that's tensile strength. Okay, the same would be true for the cohesion. Also creates surface tension on the surface of water. Okay, so it's like all the hydrogen bonds which are on the surface of water stick to each other, creating an almost skin-like effect over the top of water, which explains why structures like why organisms like pond skaters can survive by standing on the top of a pond or on a river. Okay, so that's surface tension. Okay, now water molecules can also stick to other things, which is known as adhesion, and that's very important in biology as well. Capillary action, when water molecules climb up xylem vessels, that's all due to adhesion, with the water molecules being attracted to the woody-like material in the walls of the xylem. Okay, so again, surface tension is a physical property, and we're relating that to its impact for pond skaters. Adhesion, a physical property, relating that to capillary action, which is important in xylem. Okay, the next one is the fact that it's a very good polar solvent. Because of the polar nature of water molecules, they've got positively charged ends and negatively charged ends. Okay, they're very, very good at dissolving other polar molecules. Okay, so very important solvent. Okay, and all sorts of things can dissolve in water. Probably the most useful substances which dissolve in water are carbon dioxide and oxygen. Okay, if it wasn't for carbon dioxide and oxygen having some solubility in water, life wouldn't exist. Okay, so a universal solvent, very important. Okay, another feature of water is that when it drops below 40 degrees centigrade, it becomes a semi-crystalline structure which has less density than liquid water. Okay, which means that ice floats. Okay, so water below 4 degrees centigrade starts to rise rather than sink as you'd expect it to do, and what happens, it then forms ice which is lighter than the water, so the ice forms on top of the water, which again has impact for living organisms. Okay, so it means that organisms in winters can survive in lakes and so on because the ice forms on the top rather than the bottom. Okay, and that layer of ice insulates any water underneath. Okay, ice also has an impact on floating ice. Also has an impact for Arctic organisms. Polar bears live on ice and so on. So that's another impact it has on biology. Okay. Another feature of water, which I haven't written down here, is the fact that it is transparent, and that's hugely important for biology because it lets light through, which is obviously hugely important for photosynthesizing aquatic plants. Okay, so the light can actually get to those plants so they can photosynthesize. Would be another physical property of water which has a huge impact on biology. Okay, now there's quite a nice little video here I'm going to show you, which illustrates some of those points about water.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
So moving on to the next